Hello, and welcome to our block in which we'll focus on regression analysis. Here's our visual layout of the entire course, so we can see that regression analysis is getting towards the end of our class. We're going to look at, here in block 6, at some extensions or applications of our inferential statistics to pick up a few very prevalent techniques in business data analysis. Here are our learning objectives from this block of material. We're going to start out thinking about our relationship between two variables and extend that discussion to go on and calculate what we call the least squares simple and multiple regression equations, the model equation that allows us to predict the value of one variable based on the value of one or more other variables. Along the way, we will come up with some summary measures on our model. We'll come up with some coefficients that we'll find and interpret, particularly the correlation coefficient, the coefficient of determination. And as we develop our model equation, we'll find that each of the coefficients for our variables, these are some of the critical parameters in the expression itself. These coefficients will have, we'll talk about those, and we'll talk about their significance as well. So the goal is to determine the mathematical expression for the best fitting line that captures a relationship between two variables. So some of the terminology we're using so far goes back to our initial discussion about the relationships among variables. You'll remember way back when we were talking about correlation, talking about scatter plots, we said, hey, we're interested in the relationship between two variables. We're specifically interested in here in finding out about the value of one of our variables as a function of the other. So we want to predict the value of what's called the response or the dependent variable. And if in your mind you're picturing a scatter plot, this is the one that we would put on the y-axis. So we want to predict the value of this response or dependent variable based on the value of one or more explanatory or independent variables that would go on our x-axis. So again, it's very much related to correlation analysis. And you'll recall there we were interested in knowing about the direction of the relationship. Is it a positive or negative relationship or association? Sometimes we'll use the terms direct or inverse in place of positive or negative. And then how strong is that relationship? Is it a very strong relationship, or is it so weak that we'd have to say, oh, there's not really much of a relationship at all? Well, again, this is going to be based on our material that covers covariance and correlation. You'll remember correlation gave us some numeric determination of the strength and direction of the association between our x and y variables, and we could capture this on a scatter plot, and that would give us some indication also. So we spent time with these things. Well, here we're particularly interested not just in saying, is the relationship strong or weak, and what direction does the relationship have, but we're really quite interested in understanding something about the actual line that the points are clustered around. Let me bring in my visual picture here, and you'll remember that when we were talking about scatter plots, we said, hey, if the points are clustered in this XY space in some random fashion, as you see here, it would seem there's not much of a relationship, and the correlation coefficient that's depicted here for this cluster of dots, of coordinate pair dots, is very small, very close to zero. And correlation coefficient, as you'll remember, goes from a -1 to a +1. So as these points tend to be clustered more around a line, if you could imagine a best fitting line through here that seems to have a negative slope. So these points would look as though they have a negative correlation, because the slope of that best fitting line that you could imagine running through these points, the slope of that line is negative. The correlation coefficient also is going to be negative, although its value has nothing to do with the slope. They both will happen to be negative, or they'll both be positive, but the values have little to do with each other. As the points get more tightly clustered around this straight line, the magnitude of that correlation coefficient goes to -1. So the slope is negative, the magnitude is 1, implying perfect correlation. And here, your imagination is helped very much by the fact that all these points will lie along the line. Similarly, if we went to the other extreme and looked at a cluster of points that were tightly clustered around the line with positive slope, here we have a positive correlation coefficient. We'd say the relationship is positive, and it's fairly strong, 0.944 for the correlation coefficient in this case, and ultimately it can go to the extreme of having a +1 correlation. So we're starting out jogging your memory, if you will, on the question of correlation. What we're specifically interested in regression analysis is the model equation, the mathematical equation for this best fitting straight line that falls right through these points. And in this case, the points all fall on this line, but in most cases they won't. And we need to find out what's the best fitting line through these points. And we'll spend some time in the next block, a video on this block, where we'll look at how that line is determined, and then we'll go ahead and look at the results from that. How do we interpret the results? And then we'll look at some examples.